Welcome to the non-parallel coder. Today's video is about computing the vectorized exponent function, and this is the AVX512 version of the presentation. To begin with, let's recall how the exponent can be calculated. The calculus class suggests that this can be done by computing the series. The formula goes back at least to Euler, and it is remarkable in the sense that the series converges for any value of x, no matter how large x is. However, the infinity icon as the upper limit of the sigma is somewhat disturbing. I would like to limit the number of elements of the series that need to be added. To do this, we need to limit the possible values of x. Let's try an engineering approach first. According to the IEEE 754 standard, the number 0 in 32-bit format is represented as this. Quite logical. But what about the rule that the highest hidden bit of a mantissa is always equal to 1? Well, there are no rules without exceptions. If all the exponent's bits are set to 0, the number is considered denormalized, and the hidden bit is assumed to be 0. Add 1 to the lowest bit of the mantissa, and we get the smallest positive number represented in this format. The decimal representation of this number is about 1 to the power of minus 45. Its natural logarithm is approximately minus 103.6. At the other end of the number ring is the value of infinity, which is represented by an exponent consisting of 1s and a mantissa consisting of 0s only. Subtract 1 from the lowest digit and we get the largest number, just a hair from infinity. The approximate decimal representation of this number is 3.4 times 10 to the power of 38. The natural logarithm of it is 88.7. Wonder what happens if you do not subtract but add 1 to the lowest bit of infinity. You get not a number. According to the IEEE 754 standard, if all the exponent bits are set to 1 and the mantissa is not 0, then it is not a number. Not a numbers also have an internal classification, but this topic is outside of scope for today. We will note only one curious property of not a number. It is not equal to anything. Therefore, the fastest way to check for not a number is to compare the value with itself. If we get false, we encounter not a number. Our exercises with number representation suggest a simple idea. Limit x to an interval from minus 103 to plus 88. The idea is reasonable, since an argument outside this interval will cause the result to go beyond the representable 32-bit floating point numbers, and therefore the calculation is meaningless. You can immediately say the result will be either 0 if the argument is negative, or infinity if the argument is positive. However, by my estimate, if we limit x to such a large interval, we will need more than 100 terms of the series to obtain acceptably accurate exponent values, when the factorial is known to exceed the degree of the argument and the series begin to converge. Instead, let's use a mathematical trick and represent x as an integer number of logarithms of 2 plus a remainder. Then the exponent can be calculated as 2 to the power of n multiplied by e to the power of the remainder g. We are very good at multiplying floating point number by the power of 2. To do this, you just need to add n to the exponent. And g is bounded by the logarithm of 2, which is about 0.7. This is already a very comfortable interval of arguments for calculation, and you can get by with only 8 terms in the series. Let us represent this head of the series as a polynomial, and now calculate it according to textbook formula. In addition to vector parallelism, the textbook approach also allows parallelizing calculations, for example, in lines 22 and 23, in lines 24 and 25, 26 and 27, and so on, by executing instructions out of order. The execution of the program is also slightly accelerated by the use of fused multiply add FMA instructions. In fused multiply add, the result of multiplication is added to the cumulative sum by passing the clipping of additional bits of the mantissa in the arithmetic logic unit, thereby reducing the rounding errors and saving time and energy spent on truncation of bits and subsequent reloading into the ALU. It should also be noted that the operation of multiplication by the power of 2 is so important and widespread that it deserves a dedicated machine instruction, scale F, in line 36. Let's test our code. The test verifies that the relative error does not exceed a specified value over the entire range of permissible inputs. We calculate the error not in relation to the mathematically correct value, but in relation to the result of a scalar library function. After all, with vectorization, you usually have to prove that the result of the vector code execution is as close as possible to the scalar version, which is already deemed trustworthy. While the error is more than twice the standard established from the theoretical error analysis, even fused multiply add didn't help. The reason for the accumulation of error lies in the fact that as the polynomial degree increases, the added monomials become smaller and smaller modular, and the rounding error becomes more and more noticeable. Cahen algorithm, discussed in the previous video, allows you to take into account and reduce the resulting error by performing additional arithmetic operations. Are there any cheaper alternatives? You can compensate the rounding error by representing the polynomial as a tree of pairwise additions. In this schema, closer numbers are added pairwise, which entails minimizing the error. An interesting trick is used in lines 12 to 18. The calculation of G now takes 2 fused multiply add operations, and the result is more accurate than could be achieved with any single multiplication, which is equivalent by the textbook rules for simplifying expressions. I first saw this trick in Intel open source library for the 8087 coprocessor, published around year 2000, and the trick still rules. Run the test and see that the error is now within the acceptable limits. Another good way to reduce the error is to calculate the sum from the end. Then both the sum and the next term grow at the same time, minimizing the rounding error. Improving a little bit on this idea, we come to the well-known Horner formula. The Horner schema allows calculating the value of a polynomial in a minimal number of arithmetic operations, especially if you use fuse multiply add. The code turned out to be very compact, but we lost the ability to execute commands out of order. Each command depends on the result of the previous one. Let's try to spoil the code a little bit by returning some parallelism to the code. Group the terms in pairs, factoring out the squares of x. This is similar to Horner's schema, but not relative to x, but relative to x squared. Repeat the grouping, this time relative to x to the fourth. The resulting Estrin schema requires a little more work than Horner's schema, while providing the ability to evaluate subexpressions in parallel. Now it's time to run a performance test using Google Benchmark. The tree of pairwise additions turns out to be not only more accurate, but also faster than the straightforward textbook approach. Horner's schema, despite the fewest commands, turns out to be the slowest. I can recommend it only for implementation in low-power devices, for example in wearables, where the number of operations and therefore energy consumption is a priority. Moreover, an out-of-order unit can be ripped out of energy-efficient devices anyways, to save both space on the chip and energy. Meanwhile, Estrin schema, while non-obvious and unpopular, rules. Look for non-obvious approaches. Do not forget to like this video and subscribe to the channel to be the first to know about new exciting challenges. Take care.